The Mesozoic is filled with interesting creatures, of course, the dinosaurs, but all kinds of reptiles that are flying through the air, the pterodactyls, pteranodons, etc., and then a bunch of animals, reptiles that lived in the oceans. So giant reptiles all over the place. And think about that, the large reptiles in the context of the mass extinctions that occur throughout the Mesozoic. Now, there are three mass extinctions that are of relevance for this middle era of life's history. First of all, we've already covered the end of the Permian. Remember, that's the biggest mass extinction ever. And like it says there, it clears space, literal and figurative space, for dinosaurs and other animals to evolve in the Mesozoic. Life is going good, but the end of the Triassic has a mass extinction. We're not going to go on to that into any detail here. But then life bounces back. The Jurassic is fine. There's no mass extinction at the end of the Jurassic. And then at the end of the Cretaceous, we have a mass extinction that has caused much thought, research, news items, etc., mainly because it has the unique hypothesized cause of an asteroid impact killing the life then. But let's go through the process here and talk about this end Cretaceous in greater detail. So first of all, size matters. In this diagram you have an assortment of modern rodents, and maybe they're supposed to represent Mesozoic rodents as well. They did exist with the dinosaurs, but they were these little squirts compared to, of course, the dinosaurs. And here they put a modern elephant and a modern human among a bunch of Cretaceous and other era or other period dinosaurs that existed then. And the thing is that during these mass extinctions, we didn't talk about it so much for the other ones, but I'm going to point it out in a big way here. Size matters. Preferentially, big organisms are targets. They die. So during normal evolutionary times, getting bigger is a common evolutionary trend. There's a trend towards larger and larger size, and being big is good. Being big means you can compete for or get more resources, and you're king of the hill, literally. But being big during one of these mass extinction events is the opposite. In that case, the meek inherit the earth, things like these little rodents here. So first let's look at an ocean example, and this is at the end of the Cretaceous. And I should say this too, that I will always talk about the Cretaceous tertiary boundary, or the end of the Cretaceous, as the KT. K for the German spelling or German word for Cretaceous, which is der Kreide. So that's the K, Cretaceous, tertiary boundary. Okay, so in the oceans you could imagine a scene like this, and the Cretaceous tertiary boundary is between the two photographs. There's little scale bars there for 0.1 millimeter, and what you're looking at are single-celled creatures. They're zooplankton that grow a beautiful little shell, and they're plentiful in the oceans today. They're plentiful in the oceans back then as well. And you see here that before this mass extinction event, there are small ones, medium-sized ones, big ones, truly giant ones. After the mass extinction event, we are exclusively left with the smaller representatives. So the bigger ones are preferentially extinct after one of these events. And by analogy, going back to this slide, after the end of the Cretaceous mass extinction event on land, these big taxa are gone, and what remains are the small taxa, which are predominantly mammals. So let's talk about the main hypothesis of interest. And we have to talk about these two gentlemen here, Louis and Walter Alvarez. Louis on the left, Walter on the right. They're a father and son team at Berkeley. And in the late 70s and earliest 80s, Walter, the geologist, father's a physicist, son is a geologist, father's a big physicist, a Nobel Prize-winning physicist. The son, very, very excellent geologist. And he was studying rocks in Gubbio, Italy, right at this Cretaceous Tertiary boundary. And his hand is on it. So Walter's hand sits right, his fingertips are pointing right at the boundary. And so anything lower than that would be Cretaceous rocks, and anything above it, where Louis's hand is, are Tertiary rocks. And you can see sort of a color difference here. And the other big difference is that if they look at these organisms, there is a wholesale mass extinction of these living ocean creatures there. Well, he was very interested in that, and also noticed that, all right, there's this mass extinction on land as well. Big things like dinosaurs go out and a whole bunch of other things, but he was studying these rocks, and he asked his father, is there some way to distinguish this Cretaceous Tertiary boundary without having to just look at the fossils? And also, what is a potential killer here? And Louis, being a physicist, said, you need to look at those rocks and examine them for every possible chemical element, and we'll see what we get. And they analyzed Cretaceous Tertiary boundaries in several places, and let's go back to this one. Literally what they did would be they'd take a sample every centimeter or so up through the rocks at the boundary and then across the boundary. And let's say you're looking at percentage calcium, and you'd see, well, it goes up, it goes down, it goes up, it goes down, it's random. If they found anything that wasn't random, like all of a sudden one particular element disappears, or one particular element, in this case, really gets super abundant at any particular place here, that might help answer the question. And one of the things they found was looking at the element iridium, but also the element osmium. And iridium, if they plot it up, so on this diagram here, it's very busy, I know, but on this side, on the extreme right, you see meters. So this is meters above the bottom of the mountain, the bottom of the section where they're studying. 300, and then the scale changes, 347.5, 0.6, 0.8, etc. And then over here we have time, and so right between those two arrows is the Cretaceous Tertiary boundary, and the little dots represent the iridium in the clays that they collected in parts per billion. So we're not looking at very, very much, but notice it's uniformly low, low, low through all of these, really 300 meters of Cretaceous, which is millions of years. And then right at the boundary, notice it increases by several orders of magnitude. And then it decreases again afterwards, and after some period of time it goes back like this. So something delivers iridium in a big way to the Earth right at that boundary. It coincides with the boundary. And Louis, the physicist, reasoned that, okay, iridium is rare in space, or rare in Earth, excuse me, but abundant in space, and so some space object, an asteroid, a comet, something, delivered a huge load of iridium to the Earth right at that boundary. Well, they studied it first here in Italy, and they found this interesting result, and so then they went to Cretaceous Tertiary boundaries everywhere around the globe and found it repeated all over the place. And so here are two different situations. So the lower picture is an ocean core, so a core out in the middle of the ocean. And again, you see the color difference, one color below the boundary, there's the boundary, the different color above, and then right there at the boundary is the start of a unique clay boundary. And again, that pattern was repeated. Up here, the upper picture, you can see a little Swiss Army knife in the extreme right of the picture. This was a measured section. These were rocks you could walk on out in Montana, Wyoming, North Dakota, all of those western states. And you see there's the Cretaceous rocks at the bottom. There's this very distinct black band, this clay layer, right at the boundary, and then above it the tertiary. And never forget that for all of these patterns, here we have large organisms below the event, and then what is left is very few small organisms above. In the upper picture here, you'd have dinosaurs below that knife. Above it, we never have them again. This is from their original 1980 paper. And the few black dots that you see on this map, there's less than 20 of them, but you see they're scattered all over New Zealand, the Atlantic Ocean, Pacific Ocean, in North America. They mark Gubbio, Italy, the place where it all started. And they went to all these places, and everywhere they went, all these different environments, all these different ancient environments, they found the same pattern. And so it had to be unique, and they published this paper. It became a landmark paper. They made all kinds of news. It got paleontology and geology into the public eye in a bigger way than it ever did before. And so to this point now, virtually everyone, if you'd ask them, well, what killed the dinosaurs, they'd say, oh, an asteroid did it. Well, that starts in 1980 with the Alvarez family. A little bit later, you can map all the other additional places where they have found these iridium anomalies. That's what we call this spike or this huge amount of iridium. And you see that we've gotten a bigger global coverage here, and we can map different abundances of iridium. Just suffice it to say, it's global. So it had to have been a global event doing this. Now, people began modeling all kinds of ways in which asteroids or objects can hit other objects in labs. And when you do this, you can vary the speed at which the object comes into the bigger object. You can vary the compositions of the two. You can change the angle from straight down to just sort of skipping along the top. And if you have anything within a certain range of angles here, you get this sort of situation. You have a huge crater created when this explodes into the ground. The friction is so intense that there's a lot of melt. So there's literally melting of the ground here. The explosion is enormous so that it throws up tons and tons and tons, millions of tons of debris, both sort of solid debris busted up here, but also little melted droplets go into the atmosphere and spread all over the place. Never forget this picture right here, where iridium is scattered all over the globe. After the crater after the impact, the crater recedes. There's usually a large bump in the center when they model this. There's still debris in the atmosphere, but it lays itself down, and eventually it gets deposited all over the globe. Environmentally, what you can imagine is a situation, here on this diagram, you look at temperature on the y-axis from higher to lower. The line represents sort of time before anything, average temperature before impact. And then below you have time measured as there's the impact, and then hours later, days later, weeks, months, years, decades, etc. Before the impact, business as usual, nothing going on. Right at impact, temperature is going to soar. You're going to have a giant fireball, which is what we're sort of looking at in this picture right here. This is eventually going to recede after a period of several days, maybe weeks, and then, because the atmosphere is so loaded with all of this debris, it literally is both reflecting sunlight away and also preventing it from getting in. You're going to have a period of intense cold afterwards, followed many months later by an extreme warming again, caused by now all of the excess CO2 in the atmosphere, sort of a greenhouse effect. So notice that the Earth goes through a period of intense heat, intense cold, intense heat again, and there's your killing mechanisms right there. Organisms have to adapt or die when environmental factors change. But when you have time scales like this, hours, days, weeks, months, even years, even decades, that's not enough for evolution to do its thing. And so life is hit by this and dies in huge amounts throughout the world. Okay, besides the iridium anomaly, what other evidence started piling up? The first is those tektites. Remember those droplets of melted earth that are thrown up into the atmosphere? They quickly harden again. They become thousands, billions, tens of billions, hundreds of billions, more, trillions of little teeny tiny micrometeorites. And these things scatter all over the globe after the impact as well. The pictures you're looking at here, there's some bigger ones. Here on the lower picture, the tick marks are all centimeters, but the upper picture, these are all millimeters. And these little balls are found in huge abundance right at this Cretaceous Tertiary impact site. Soot. Soot, when you burn a campfire, you've got the smoke, but also just that solid particle, the soot that comes from burning the forest. Well, think about it. If you're going to create a huge fireball somewhere on planet Earth, you're going to ignite large areas, huge, thousands and thousands of square miles of forest vegetation cover, which is going to produce a huge amount of soot. Global fires. It turns out when we measure soot, it is particularly abundant at this KT boundary as well. And this can be quite just enormous. Imagine this. So this picture on the extreme right is a satellite photo from a series of fires up in Canada in July of 2002. You can sort of see the outline. Here's the Atlantic Ocean. Here's some of our United States. There's New York, Pennsylvania, Maryland, Virginia, West Virginia. Here's some of the Great Lakes, Ontario, Erie, Huron. The fires are way up here up north in Quebec in these little areas marked by the orange site, and you can see the slightly grayer, darker smoke. There's white clouds on either side, but you see the darker smoke from these little pinpoint fires up here traveling all the way down and creating extremely smoky conditions in our northeastern part of the United States. These were very hazardous times, and there are actually some people with lung issues, emphysema, high asthma, lung cancer, etc., that died from excess smoke inhalation during this time. And this is just from these smaller fires. Now imagine thousands of square miles of forest ignited during one of these asteroid impacts, and you'd see that the Earth would have huge amounts of smoke, huge amounts of soot. That could also be a killing mechanism. If we plot it up, we have this situation here. Hold on. Sorry. We have this situation here where this slide's just messed up. You see the situation here where iridium has its spike. That's the figure on the left. So remember, iridium, you deliver this from space. Soot, plotted over here in parts per million, also has a spike. What else? We have this thing called shocked quartz. Now, quartz is one of the most abundant minerals on planet Earth. It's silicon dioxide. And if you've ever seen or collected or walked through sand, you've probably walked through quartz, because most of the sand on planet Earth is quartz. And quartz normally under a microscope wouldn't look like this. It wouldn't have these very distinct lines. You can see these lines sort of going up and down this way and side to side this way. Quartz can only get these lines if it has been hit or impacted or put under extreme pressure to do this. And so shocked quartz, when you plot it up, it also has a spike at this Cretaceous Tertiary boundary. So it fits. So notice all of this evidence starts lining up that some object from space, rich in iridium and osmium and other space elements, hits planet Earth during this time of the dinosaurs. And so you see this ceratopsian dinosaur and this T-Rex here, and they're sitting here as death is coming. This hits the Earth. It starts this cavalcade of environmental reactions. You have the huge temperature increases, decreases, increases again. You've ignited global wildfires that are depositing soot everywhere. The tektites are raining down globally as well. It's a horrific time. Shocked quartz is raining down. Everybody started buying it, believing it. But then the next question is always, where is the crater? Searching around the globe for the crater became a drive for thousands of scientists of all types. Not just geologists and paleontologists got interested in this, but biologists, chemists, physicists, astronomers. The grant money flowed like water, and everybody jumped in on this looking for the crater and more evidence to support or falsify that hypothesis. And there are lots of craters on planet Earth. So this map here shows dots of known craters scattered throughout North America. There's several hundred of them all around the globe if you add them all up. But you have to have a crater that, when we age date it, the rocks that it hits and the rocks above it, there has to be a crater that hits this time, this 65 million year period. After a couple years of searching, the crater was found, the smoking gun was found in Mexico. So if you've ever been to Cancun or Cozumel, Mexico, you've been on the beaches above this crater. It's not visible on the surface. It is entirely in the subsurface. 65 million years of erosion and sedimentary deposition have completely covered it, but the Pemex, the Mexican oil company, has drilled all kinds of holes through there, and they've mapped it out, and it's a crater that is huge. It's huge. It's several hundred or a couple hundred miles in kilometers in diameter, and it's rather deep. It has the exact right time. It's in a place called Chicxulub. I know it's spelled really crazy. And when we do the modeling then of the size of the crater, the location of the crater, there it is in Mexico, and then where we have measured iridium anomaly all over the place and all this, we now have we know, in fact, that this asteroid came from this trajectory at an angle of about 25 to 28 to maybe 30 degrees and hit right here. The bulk of that blast then would go straight up to North America. And so we in North America actually, besides the crater area, have the largest destructive evidence of this event anywhere. So this created enormous tsunamis, 100 feet or more high. It spewed all of this death and destruction, iridium, everything, all over our area where our dinosaurs were. It was considered a done deal. An asteroid did it. The evidence suggests it. That's it. A few years later, a group from the East Coast, mostly Princeton University, but a couple other universities, said, you West Coast people, you Berkeley crowd, are wrong. You don't need to invoke some object from space if there's a simpler explanation right here on Earth, volcanoes. And they said at this exact same time, this 65 to 66 million years ago, the Deccan Traps, it's this area in India, had explosive volcanic eruptions that are exactly timed at this time as well. It turns out that when they started doing this, they discovered, volcanoes also will belch out huge amounts of iridium. So it's not just that iridium is rare on Earth, it's rare on the surface of the Earth. So if you evacuate a magma chamber like you've done here, you'll produce high amounts of iridium. If the eruptions are explosive enough, you'll produce the shocked quartz. If the eruptions are explosive enough, you'll ignite the fires, and so volcanoes can do everything that you're saying this asteroid could do, but we have a simpler earthbound hypothesis. The volcano crowd started trying to impress the public as much as the asteroid crowd, so they hired their artists to portray volcanoes doing all this stuff and killing dinosaurs, and it became a very vociferous argument between the two groups. Which did it? What was the killer? Meanwhile, all this research continued on, and our astronomer friends started looking at impact objects and impact scars. And you've got places like the moon that are riddled with tectonic craters that have not been erased by erosion because they are on a planet that doesn't have much of an atmosphere at all, doesn't have flowing water, so they're preserved. And they could see this this relationship between the lunar maria, which are huge volcanic fields, and these craters. And this hypothesis of, hold on, let's erase these. These hypotheses of craters sort of somehow having a relationship to volcanic activity brings up this hypothesis of the antipode. So if you have an asteroid or an object hit our model, our computer model here, it's going to send shock waves through the Earth. We've already talked about this when we talked about tectonics. They're going to bounce all around, they'll emerge everywhere, but there'll be a concentration of them at what we call the antipode. And the antipode is on the other side of the planet, 180 degrees away. Boom. Lots and lots of shock waves over here, enough to perhaps force volcanic activity. If we look at other rocky bodies throughout the solar system, if we look at Mercury, there's a giant crater. Look at this, over 1,000 kilometers diameter, the Caloris Basin. The outer rim of it, it looks just like, not much here, but the outer rim are mountains, 3 kilometers high. And on the opposite side of Mercury, 180 degrees away, is a chaotic terrain of volcanics. So it's evidence that this impact caused this antipodal volcanism. If we look at Mars, Mars has a giant crater, this Hellas Planitia, and if we go 180 degrees around the planet, there is this enormous volcano, Alba Patera. So antipodal volcanism exists. There's evidence on these two other rocky bodies that large impacts force volcanism on the other side of the planet. The solution then is, there it is. There is the asteroid impact in Chicxulub right there in Mexico. It's kind of hard to see with this map distribution, but India is on the other side of the planet at that time, about 180 degrees away. And so there was this great meeting of the minds, and the idea now is that both are responsible. That you have this impact causing all this death and destruction here almost immediately on the other side of the planet. It ignites or reignites volcanic activity here, which does its own death and destruction number in its local vicinity. So would this have caused the extreme mass extinctions alone if the asteroid impact didn't happen? Probably not. But if you add this 1-2 punch together, they're taken to be both responsible. Half an hour and we've covered the Mesozoic end Cretaceous mass extinction.